Thank you. Hello, everyone. My name is Megha, and I'm working on understanding the properties of remnants that are formed by stars getting disrupted by supermassive black holes. So, firstly, what are supermassive black holes? They're just black holes that have mass much greater than or equal to a million solar masses, and like it has been proposed that they should exist in the center of most galaxies. This picture here shows the supermassive black hole of our own galaxy Milky Way, which was taken last year. So these black holes are surrounded by stars, and sometimes they come close to the black hole and get disrupted. And as was mentioned in the last talk, we can have two types of tidal disruption events. One is like a full tidal disruption event, and the other one is a partial one. So the tidal radius is actually the distance at which the gravitational forces of the black hole can overcome the self-interaction forces of the star. So this formula here basically is a very Newtonian approximation of a tidal radius. It doesn't consider the internal structure of the star or the spin of the black hole or the star itself. But it kind of gives like an approximate distance at which we should expect the star to be disrupted by a supermassive black hole. So the tidal disruption events were first proposed in 1970s, and they were detected in 1990s first detected by Rosette All Sky Survey. It is expected, like it is theoretically and observationally determined that these events should happen once per 1,000 to 10,000 years per galaxy. And we have also found some partial tidal disruption events in the past couple of years. For example, these ones that have been detected. If you're interested in understanding how these events are observed, you can refer to Ghazari 2021, which gives a review of how these events have been detected in the past couple of years. So my project basically focuses on understanding the remnants that are formed by partial tidal disruption events, where the star gets close to the supermassive black hole, but the black hole is not strong enough, like the tidal forces of the black hole are not strong enough to completely rupture the star apart. So we are just trying to understand these remnants. And to do that, we have used two different codes. One is called Kepler, and the other one is Phantom, which we are like all this using here. So the Kepler is a one-dimensional stellar code written by Woosley, and it is maintained by my supervisor, Alexander Heger. So we brought generated models in Kepler, then we bring them into Phantom, and then disrupt our stars in Phantom, and then write a file which contains the properties of the star. And then we bring it back into Kepler and evolve the models to understand how the evolution of the star might change after interacting with the supermassive black hole. So I will firstly explain my pipeline. So for my project, I'm using three different stellar models: one solar mass, three solar mass, and 10 solar mass at three different stages of its life. So we are using zero age main sequence, the mid, which is about half, where half of the hydrogen has been used up in the star, and then the depletion, where the star has almost used up all of the hydrogen in its core, which we also call the terminal age main sequence. And this just shows the HR diagram of these three models that I'm using. So these three models are then brought into Phantom, and we basically read the information from the one-dimensional code that Kepler generates, and we bring it into Phantom, and then we perform a relaxation procedure that was outlined by Mike Cloud today in the talk as well. For our simulations, we are using 1 million particles, and all the models are set on parabolic orbits. We are considering general relativistic effects. We have found that the general relativistic effects lead to the parabola, the pericenter to be much closer to the star, to the black hole, compared with what we get from the Newtonian formula that I showed earlier. So there is about a 6% error. And for all of our simulations, we have used a spin of 0 and black hole of 1 million solar masses. Something that I should mention is beta parameter, so which was discussed in the last talk as well. It is the ratio of tidal radius with the pericenter distance. And in our simulations, we basically have tried to run different beta parameters until we find a boundary where the star is fully disrupted. For this model, this is a one solar mass ZANS zero age main sequence model. We found that the maximum partial tidal disruption event can happen until a beta value of 1.4, and after that the star is fully disrupted. So this first movie, it basically shows a beta of 0.5 getting disrupted. The star only uses about like it only use so out of it still has about 99% of its mass left. And the second model is a beta 1.4. So the star is completely ruptured, but then material starts falling back again. And then after quite some time, it starts looking like a sphere and spherical body. So something that I should mention here is that these simulations still have a couple of particles around the star, which are still trying to get away from it. So we are still running them for much longer time before we write our results for the first publication. So once these models have been run, next thing is that we want to bring these models back into Kepler for evolving the models. So to do that, we have written a binning method in Phantom in the file called analysis Kepler. So the binning method basically considers the point of maximum density as the center of the star. And then based on like sorting by radius, we bin the particles by mass. So every bin has a same mass. Another condition we have imposed is that particles which have energy less than zero, so energy EI here is the sum of kinetic and potential energy. So particles which have less than zero energy are considered as being part of the star. Otherwise, they are considered as material that has been stripped away. This plot here basically shows the comparison of our binning method with the Kepler model that we are working with. This is also for a one solar mass ZAMS. So when we bring model into Phantom, we lose the outer layers during the relaxation procedure. So that's why we don't have like the bins around there. But other than that, this method works pretty well. So we have written files for different stars based on this binning method. And here we just show the properties of a one solar mass model, zero age main sequence, which was disrupted at different beta values. I'm just showing 4 here, and the mass of the remnants. As you can see, the 1.4 leaves behind a remnant of 0.14 solar masses. So it is an extremely very small star. And then 0.5 is still pretty much a one solar mass remnant. And also the density of the star also decreases as the beta parameter becomes higher. So once we have written the performed the binning method, written some files, we are trying to bring them back into Kepler. So this one here is a Kippenhahn diagram of a one solar mass star. The x-axis is times in gigayears, and the y-axis is the mass of the star in solar masses. So basically, this shows like the evolution of a one solar mass star without bringing it into Kepler. So what we expect is that there should be a convective layer in the outside regions, and then around the 11 billion gigayears, the star becomes a red giant. So there is hydrogen burning in the shell there. So with our model, therefore, so this one shows a one solar mass model, which wasn't disrupted in Phantom. So we just brought it into Phantom, relaxed it, and then map binned it and brought it into Kepler, and then evolved it to see if we can like get a match between the two models. And it's very clear that we are missing the outer convective layer in this model, and then the time period of hydrogen burning in the shell is also much longer. So we are trying to fix that. And one explanation for this is this initial model basically considers rezoning of the layers of the regions. But this one, this model that I've used, it doesn't. So we are still trying to fix it. And the future goals of my projects are to finish up my 1 million solar particle simulations, and then fix the Kepler issue that we are currently having, and then start running binary disruptions to understand how they might impact the evolution properties of the remnants. Yeah, thank you.
Does anyone have any questions? Yep, I'll just start here. Thanks for the interesting talk. So, have you, when you reconstruct you had the binning method to reconstruct the 1D profile, you show the density and chemical composition, but did you look at the thermal profile? Like, you probably did to reconstruct the star, but I'm interested in how much tidal heating there was upon the encounter, because there should have been some heating, or even if you have tidal and partial disruption, some of it rains down, you have a higher entropy profile. And did you look into these things?
We haven't looked into the temperature profiles yet, but
Yeah, that I would be personally interested in looking at those. So yeah, let's see later.
Have you also looked at the rotation of the star? Is it significantly rotating after the partial TDE?
Yes, we have looked at the rotation, and what we have found is for very strong encounters, the outer layers have differential rotation. So, but the core is still like rotating at a similar rate. So we are still trying to like, going to try to fit a polynomial to see like what is the differential rotation like curve, and then yeah, I'm also trying to plot it into 3 dimensions to understand how exactly the outer layers are rotating after the disruption event.
So do you expect that this rotation signature would have a observationally significant like a signature, or is it too short before the angular momentum transport sort of spins down the surface again?
I have to look into that a bit more.
Okay, so thanks.
I'm not sure.
Any other questions? No? Okay. Otherwise, let's thank Megha again for the great talk.